Resume recording. So we are changing gears completely, like I said last time before my internet died, or maybe you guys didn't hear it, but we're done with waves. We're done with optics. We're done with lenses. We're done with all of that. We're changing gears completely to the second half, really. It's the second third, or the last third of the course. We're going to be talking about thermodynamics. Now we're about a lecture behind, or maybe half a lecture behind, and that's okay. We just won't cover everything that I would like to cover, and I'll just adjust the last exam accordingly, so don't worry too much about that. But we're going to be talking about thermodynamics basically for the rest of the course. So thermodynamics is really just the physics of thermal energy. And so anything that involves thermal energy, you can imagine that we might cover it in the next 2 weeks. So first, we're going to talk about temperature. So temperature, which is section 5.1, or this discussion can be found in section 5.1 of LibreText, is a relatively physical thing, and it shows up a lot in everyday life, so it's useful to have a good understanding of what it is. So before we can actually define what temperature is, and talk about what temperature is, we need to back up a little bit and give some definitions. So let's talk. So first definition is the phrase, or the term, thermal contact. So thermal contact is when two systems are allowed to exchange thermal energy with each other. Directly. So that's what thermal contact is. So anytime you have two things able to exchange thermal energy, that is, those two things are in thermal contact. And just because they are able to exchange thermal energy doesn't mean that they are exchanging thermal energy. So another definition that we need is thermal equilibrium. So two systems are in thermal equilibrium when two systems that are in thermal contact exchange zero net thermal energy. So that would be an example of two things being in thermal equilibrium. If they're in thermal contact, but they're not exchanging thermal energy, or rather the net exchange of thermal energy is zero. Now, with these two notions, we need thermal contact to describe thermal equilibrium. Sorry, we need the notion of thermal contact in order to describe thermal equilibrium. So with that notion of thermal equilibrium, we can actually talk about the zeroth law of thermodynamics. Now, it was called the Zeroth Law of Thermodynamics because it was come up with after the first, second, and third, but it didn't seem, but it's kind of so fundamental that they didn't want it to be like some random number, so they called it zeroth, just because it's almost definitionally true. So that's why it's called that. So the Zeroth Law of Thermodynamics states that two objects in thermal equilibrium, two objects in thermal equilibrium. Remember, that means that they're in thermal contact. That's not how you spell equilibrium. They're in thermal contact, but they're not exchanging thermal energy, have the same temperature. And vice versa. If they have the same temperature, then they are in thermal equilibrium. So this is like almost obvious. And really, it's basically just a definition of temperature, right? It's basically just a way of saying, look, the way we define temperature is that these two things have that same temperature if they are in thermal equilibrium. That's all the Zeroth Law of Thermodynamics is. And that's why it's called the Zeroth Law. It's not really like a relationship between observable things. It's kind of a definition. But the point is that temperature is an indicator of whether thermal transfer will occur between two objects that are in thermal contact. So for example, if two objects are not in thermal equilibrium, then according to the Zeroth Law of Thermodynamics, they have different temperatures. But if they're not in thermal equilibrium and they are in thermal contact, that means that the net thermal energy exchange is not zero because they're not in thermal equilibrium. So if their temperatures are different and they are in thermal contact, then there will be an exchange of thermal energy. So it just says that temperature is the measure by which we check whether two things will exchange thermal energy. And if so, if they will, what direction is that thermal energy exchanged in? But before we can actually answer that second question, I want to, let me make this a little bit bigger. I want to ask a slightly different question that we also need to know, which is how do we measure temperature? Now you might say with a thermometer, but then I would ask, well, how do you put the markings on the thermometer? How does this work? Like, how did the first person to measure temperature do it? So the easiest way to do it is with relative temperature scales. So right now, as far as thermodynamics is concerned, we only care about whether energy is transferred or not. And so all that means is that if there's a difference in temperature between two objects, then there is energy transfer. And if there's not a difference, then there is not a transfer of energy. So this is just to say, at the moment, and this won't be true later, but at the moment, we really only care about temperature differences. And so because we only care about temperature differences, i.e., is this one higher or lower than that one, we only actually care about the relative temperatures. We don't care about some notion of absolute temperature. We only care is, does this one have more temperature or less temperature than some other thing? And so the way that we determine this notion of relative temperature, the way that we determine relative temperatures at all, is by picking a reference temperature or reference temperatures too. And then just deciding on a scale. This would be like saying, look, we say that that 1 foot tall is the length of my arm, and 6 feet tall or whatever is the height of my body. And so then we just say, oh, well, it's like twice as long as my arm, but half as long as my body. So, but slightly less than half as long as my body. So we can use those reference temperatures to figure out how long a foot is. Or sorry, how long an object is relative to 1 foot being the length of my arm and 6 feet being, well, 6'2" being the height of my body, right? So we can use references to determine relative magnitudes of quantities. And so these reference temperatures are actually just arbitrary choices, right? So what one could in principle choose, and by the way, we often want to choose two because that's how you need 2 points to form a line, and we want this to be a linear scale. So you might choose, say we choose that water freezes at 0 degrees. And then let's say that water boils at, say, 5 degrees. Those are choices that we can make. It's just an arbitrary choice. I've just decided that 0 is the number that we say temperature is when it's the same temperature as when water freezes. And 5 degrees is the temperature that we say something has when it's the same temperature that water boils at. And so now we have a scale. If the temperature is slightly hotter than the temperature where water freezes, but much, much colder than the temperature where water boils, then you would say maybe it's 0.5 degrees. And so these two numbers determine a scale. And so maybe we call this the Blitz. So it'd be 5 degrees Blitz is the temperature where water boils. And so it would be written, say, X degrees BZ, or something like that, right? You can just choose some arbitrary choices, make your scale, and that's a scale. And so in this scale, the human body, at least the normal human body, I'll leave that for you to figure out. The human body temperature is 1.85 Blitz, or 1.85 degrees Blitz, right? Like that's just a thing. So we know that it's 1.85 divided by 5, like the temperature of the human body is, whatever 1.85 is relative to 5, because hotter than the temperature of that water freezes out, right? Like it's just a way that we can choose a scale. Now it is not necessarily easy to figure out this ratio, right? That takes a little bit more work, but once you have a method of figuring out where on a scale an object is, which you can do by using a few different methods, which we're going to talk about, then it doesn't matter what your scale is. Your scale is just you pick 2 points and then you fit everything else on a line between those two. Yeah. 4 out would be 80 degrees Celsius. So 4 degree splits would be 80 degrees Celsius, which would not be a good time. Be careful if it's that hot outside. Anyway, however, there is a more widely used scale, or more widely accepted anyway. The Blitz will be accepted eventually. It will win out. Is the Celsius scale. So the Celsius scale says that water freezes. Come on, scroll please. Water freezes at. Just you wait. The Blitz will come to its own. Water freezes at 0 degrees Celsius, and it boils at 100 degrees Celsius. And I'll leave it up to you to decide which one's more useful. I think that the Blitz is more useful. You need less numbers. Why use 100 number when 5 number do trick, right? And then there's, alternatively, the Fahrenheit scale. Did I spell that right? Yes, I did. So in the Fahrenheit scale, water freezes at 32 degrees Celsius, 32 degrees Fahrenheit, and it boils at 212 degrees Fahrenheit. Now, how do the people making the scales know that the temperature the water boils? Oh, okay, no, that's a good question. So the point is that they had this notion of, they had ways of determining that 2 things were the same temperature, certainly, right? Just by putting them in thermal contact, they could check if 2 things were the same temperature. And so then it was just a matter of, well, it was just a matter of subjective experience, right? Is the temperature of water when it freezes always the same? And they guessed, and I'm speculating here, but I'm speculating that they guessed, and it turned out that their guess was correct. And then similarly, they figured out that you had to add roughly this, like if you had, you know, a liter of water, you had to add a certain amount of heat. You had to put it over a fire for a certain amount of time to get it to boil. And if you had 2 liters of water, you only had to put it over the fire for twice as long. And so they concluded that, yeah, I mean, the temperature of the water, how hot it was the same regardless of the amount of water that you had. And similarly, they could do the same thing with, like, if you heat up metal really, really hot, they could say, oh, well, when iron is at when iron glows at a certain brightness, it seems to always glow at that same brightness when we add the same amount of heat to it. So this is just to say that they had this notion that things don't change, like the properties of a thing depend on the material and they don't depend on the circumstances. And so, I mean, but in principle, yeah, that's a hard thing to figure out, right? Especially if you're working with very limited knowledge of physics. Now I want to back up, or not back up, but I want to defend the Fahrenheit scale really quick. I know that, like, I talk down about this, the imperial units or British units all the time, like who uses feet, who uses, you know, what are the pounds and stuff. I mean, in the United States, we use those all the time. But Tracy, we'll talk about that in a minute. But the point is that the Fahrenheit scale was created in Europe. And the reason why it has the scale that it does is because it uses, rather than saying, oh, 32 degrees is so arbitrary for water freezing and 212 degrees is so arbitrary for water boiling, but that wasn't the reason they chose that scale. They chose the scale because they said, well, 0 degrees is about the coldest that it ever gets where humans live, and 100 degrees is about the hottest that it ever gets where humans live. So they just said, well, on the coldest day, it'll be 0 degrees Fahrenheit, and on the hottest day, it'll be 100 degrees Fahrenheit. Now, this was in, like, England, I think. I think Fahrenheit was an English fellow. So it really doesn't get much hotter than 100 degrees in England. I mean, it does now because of global warming, thanks Al Gore. But, you know, the point is Fahrenheit uses the 0 to 100 scale as measuring human experience. So, and the fact that it's a wider range, it spans 180 degrees from water freezing to boiling rather than 100 degrees, means that you can be more granular. And because our sense of temperature is very, very fine, like humans can very easily tell the difference between 1 degree Fahrenheit, right? We can tell if something is hotter or colder than our skin temperature by 1 degree. It's useful to have a more fine-tuned temperature. Like I don't know if you guys ever have control of your own thermostats, but like 73 degrees can feel a lot different from 74 degrees. Whereas and so it's good to have a more granular or a more fine-grained temperature or temperature scale for human experience, because then you can make those small adjustments rather than, say, going from what like 20C to 21C. That's a pretty big swing in temperature if that were on a thermostat. So there is good use for Fahrenheit. It's just not the standard because it was, well, basically because of the French Revolution is what it boils down to. Now, like I said, so these are just temperature scales, but you also need to measure temperatures between freezing and boiling. So the question then is how do we measure temperatures between these reference points? So the way that we do that is by measuring the effects of the temperature change. So when the temperature of an object changes, there's more than just the temperature changing. More things happen. So one particular effect of the temperature change is that, example one, actually I won't write example one because that's confusing. I'll just write a star, is when the temperature changes in a gas, they cause a change in pressure for a fixed volume. So if you put some amount of gas in a box, and you heat up the box, the temperature in that box, and you increase the temperature of that box, the pressure in that box will increase. And so we can actually just graph this for different gases. And we see, and this can be done experimentally, by the way, we can just graph this experimentally. So if we have temperature on the horizontal axis and we have pressure on the vertical axis, say for one gas, maybe you measure that line. You get a whole bunch of different temperatures, you get a whole bunch of different pressures, and you can measure the change in you can measure the how the pressure changes with temperature, and it works out to be linear. And similarly, maybe you do another gas and you get I don't know, this line. Maybe you get another gas, you get this. Sorry, I can't draw a straight line. You get this line, and you're really only measuring down to a certain temperature because maybe you're in the 1800s and you don't have the equipment to get particularly cold things. So you measure down to maybe 0 degrees Celsius, right? Maybe that's the best you can do. But you keep doing this for a whole bunch of different gases, and they all have different slopes. The different gases have different slopes. But what you find is, miraculously, if you were to continue these lines, they would all intersect at a single point, somewhere else, somewhere at some very, very low temperature. The graphs all converge here. And this is generally true for every gas. So the observation is that, or rather this observation suggests that there is some absolute zero temperature which doesn't care about the substance that you're talking about, because these were 3 different gases. So if we had just chosen one gas, maybe we would have said, like for example, with water, we said, well, okay, we made the 0 of our scale 0 degrees when water freezes, but that's a peculiar property of water. But by observing that all of these different gases, they all have this property that if we continued the line down, their pressure would be 0 at some particular temperature. Well, that suggests a more universal property here, that there's actually something special about that temperature that is not dependent on material. Now, you might say, well, maybe it's dependent on the fact that these are gases. And sure, you could in principle be right. But it does at least suggest it. And so what we can do is we can redefine our 0 point. So rather than saying 0 degrees Celsius is our water freezing temperature, now we just say, we define a different scale. We define the Kelvin. Oh, by the way, just to back up, one way that you can measure one way that you can measure the temperatures between reference points is, say, by figuring out what pressure a gas should be at when it's in thermal contact with another one, and then you can measure the pressure, and then you could find along this chart, well, where along this chart is its pressure, and then what should its temperature be by using this graph, right? So that's how you could measure temperature. But more so than that, these graphs are useful because it lets us define this notion of the Kelvin. Now, the Kelvin is a unit of temperature, just like a degree Celsius, but we don't say degree Kelvin. We just say Kelvin. So there'd be 7 Kelvin, 23 Kelvin, 598 Kelvin. Yeah. So we do observe this, although it gets like obviously there's measurement error and things like that, and uncertainty and things. But yes, there is roughly an absolute zero, even with that you could do this experiment for. Now you have to make sure that these are all in the what is called the ideal gas range. So you can't like create a plasma and you can't freeze these things. But yeah, this is generally true. Right. So it's a unit of temperature. We don't say degrees Kelvin because in the same way that we don't say degrees meters, right? It's an SI unit. It's part of the SI unit system, and so we don't say degrees. Degrees are only useful for units where they are not SI units. And so if we define 0 Kelvin, which would be abbreviated K, we define that to be at the temperature of absolute zero. And then we need 2 points to make a reference temperature, but we want our 1 Kelvin range to be the same size in temperature difference as 1 Celsius, because we'd still like the boiling point of water to be 100 Kelvin higher than the freezing point. So we just choose the same. We just choose 3 points, and then it's just this 0 point just amounts to a shift. So we choose 273.15 Kelvin to be the temperature where water freezes. That's just the number that we choose. And by the way, that was determined just by looking at, well, in Celsius on this scale, this point of convergence happens to be negative 273.15 degrees Celsius, right? That's how that was determined. And then in this scale, that would mean that the temperature where water boils would be 373.15 Kelvin. This would be where water boils. So the size of 1 Kelvin is still the same size as 1 Celsius. So like if you're talking about differences in temperature, a difference of 1 Kelvin is the same as a difference of 1 degree Celsius. The Kelvin is just useful because it gives us an absolute reference point that's independent of measurements of water and so on. And so we can actually just relate Kelvin. So Kelvin is degrees Celsius plus 273.15. They're the same otherwise. It's just you're just adding a number to your Celsius measurement. So like a human body is 27 degrees Celsius, I think. So it would be like 300.15, or you guys, some of you, I don't know what the temperature of the human body is. I don't remember what it is off the top of my head, but yeah, you can figure it out just by adding 273.15. So that gives us an absolute temperature scale. And in principle, I suppose you could come up with other absolute temperature scales, but this one seems to be pretty universal. There are properties about the kelvins, or there are properties that hold for other non-gaseous substances that also do strange things or do interesting things at 0 Kelvin, or as you get closer to 0 Kelvin. And yeah, Kaushik, that is correct. The coldest temp, and this is a law of thermodynamics that we'll get to later, but one can't even in principle get a system to be 0 Kelvin. It's just not possible. And again, we will talk about why later. And so the coldest that we can make things is we can get things really, really close by using high-tech refrigerators, basically. But the closest we've gotten is to like a few millikelvin, I think, which is just a few thousandths of a Kelvin above 0. Right, so this is one way to measure temperature differences, or to measure temperatures between the reference points, by using gases, right? You can measure pressure, you can measure the pressure of a gas with like a scale, and then you can determine the temperature. There's another way to do it, which involves thermal expansion. And this way of measuring temperature differences is a little bit more straightforward and more commonly used. So thermal expansion is discussed in detail in section 5.2. So take a look there. And so thermal expansion, I mean, as the name implies, thermal expansion is the expansion or contraction of an object, of solids and liquids in particular, because gases just fill the substance that they're in, or fill the container that they're in. It's the expansion and contraction of solids or liquids when the temperature changes. So it's relatively straightforward to observe, like, well, maybe not actually. What would be a good example of this being observable? Okay, maybe you guys wouldn't have observed this on an everyday basis, although you will have seen an example of this that I'll get to in a minute. But I mean, it is true that if you have like a well, if any of you guys have done any like engineering maintenance of things or things that involve like really tight fits without fasteners, you can do something called a temperature fit, where if you have one thing, yeah, train tracks do this. Yeah, if you have one thing that you need to fit inside another thing, you can heat up the one thing so that it expands, and you can cool down the thing that needs to fit inside it so it contracts, put them together, and then let them both come to thermal equilibrium. The cold thing will re-expand and the hot thing will recontract, and they'll be stuck together really, really tightly, so tightly that you couldn't pull them apart unless you basically like applied an enormous amount of force. So that's an application of thermal expansion and contraction. It's certainly useful. So why does this happen? Well, to understand this, we have to understand thermal energy. So thermal energy is, I mean, well, have we talked about this? You guys should have seen this in 9A, when you talk about the thermal energy of a system increasing when there's friction done on the system, for example, or when there's work done by friction on a system. So thermal energy is a macroscopic, meaning observable on human scales, manifestation of microscopic motion. So you guys probably, maybe you don't know this, but maybe you do. At a very, very small scale, like at the atomic scale, at the molecular scale, everything's always moving, like everything's in motion. You have molecules jiggling about and moving and all of that business. And so that microscopic motion, it's all random. And so the point is that random motion, there's an energy associated with those particles moving. And that energy is lumped together into a macroscopic phenomenon called thermal energy. Now that motion can be broken up into kinetic energy as usual and potential energy. You have two objects, like if they're attached by a spring and they're jiggling, there's potential energy and kinetic energy. And these are of atoms and molecules, depending on the system. And so a consequence of this observation that thermal energy can be viewed as as just a macroscopic measure of a microscopic phenomenon is that the more energy that there are in the oscillations, the microscopic oscillations, this is things like if the particles in the oscillations are moving faster or have more potential energy, this implies that there's a higher average separation between those two objects. So for example, let's say that you have two particles that are bound together by a spring. Like you zoom in really, really close onto a lump of metal, and you see just two atoms. And they have a bond together, a bond between them, which can be roughly modeled as a spring. It's actually using the Leonard-Jones potential is how you would model that. And the more energy that oscillation has between the two atoms, the higher their average separation becomes, which is to say that the system expands. So this means that the more thermal energy a system has, the larger the volume is. Because the distance between the particles that make up the object is larger. If all of the distances get larger, then the whole object has to get bigger. And this is true for reasonably low temperature changes. Like if you change the temperature dramatically, then you can start to have chemistry and you can start to have chemical and physical processes occurring, which can change the volume in a more dramatic way. For example, you guys may have heard of different forms of ice. There's things like ice, there's ice 1H, there's ice 2, there's ice 3, all the way up to like ice 13. These are different atomic structures of ice. And so even though they're all frozen water, they have different, like their molecules are arranged in different ways. And so they will have different volumes and different densities and so on. And those will occur at different temperatures and pressures. So as long as the pressure changes and the temperature changes and all of those things are small, like on a relatively small scale, not so you're changing phases and changing types of objects, then this statement is true. But once you get to large changes in temperature or large changes in pressure and so on, then you can start seeing different phenomena. And so we can actually express this property mathematically. So remember that thermal energy is just a measure, or rather temperature is just a measure of thermal energy, because if two things have the same temperature, then they are in thermal equilibrium, and so they don't exchange thermal energy. So again, temperature is a measure of thermal energy. And so we can express this statement that I just made mathematically. That is, delta L over L naught equals alpha delta T. Now we have to break this down a little bit. So delta L is the change in length of an object. So if you have an object of length L and it changes to length L plus 2 centimeters, then delta L will be 2 centimeters. This L naught is the original length of that object. By the way, we're just talking length for now. We're going to talk about volume in a minute. This alpha, this is something that's called the coefficient of linear expansion. It's just a number. Well, it's a number with units. The units of alpha are inverse kelvins or inverse degrees Celsius. Either one's fine. And they're interchangeable here because we're only talking about changes in temperature, and 1 Kelvin is the same as 1 degree Celsius. So that's why they're interchangeable. And then this delta T, this is the change in temperature over which this expansion occurs. So the idea is if you know the alpha of an object, and this is just a number, it's just a number that, like, iron has an alpha of 1 of something, and steel will have an alpha of something else, and copper will have an alpha of a third thing. If you know this alpha, which you can just Google or you can measure experimentally, and then you change the temperature of your thing, your object, by, say, 5 degrees Celsius, then you can calculate the ratio of the change in length divided by the whole length. So if the whole length is, say, 20 meters, then then it will expand twice as much. It will get twice as, like, the amount it will expand by will be twice as much compared to something that was only 10 meters long. So this change in temperature tells us how the ratio, or how the relative size changes. It tells us the percentage that an object expands by. And so we can actually just rewrite this, perhaps in a friendlier way. So we would have that delta L is equal to alpha times L naught times delta T. So this would tell you how much the length changes by in terms of the original length, the change in temperature, and the constant. But delta L is just the final L minus the initial L, meaning it's the final length minus the initial length. So that's equal to alpha L naught delta T. Sorry, that should be L naught, not Li. So that they're the same thing. And so this just tells us that LF, the final length of an object, is 1 plus alpha delta T times the initial length of the object. So this is just a way to compute how long an object is when you change its temperature by a certain amount. And so you can go check this with, like, iron. You can go check this with train tracks, right? Train tracks are going to get longer if it gets hotter, and this can cause train tracks to break, actually, and to bend. Now there's a few examples that I linked to that would be an application of this type of calculation. So I suggest you take a look. But by the way, this phenomenon that objects expand by predictable amounts when you add when the temperature increases by a predictable amount, that's a way to measure temperature. Because, for example, if you have a rod that you know the length of when it's, say, room temperature, or maybe you know the length of it when it's 0 degrees Celsius, and let's say you also know what alpha is, then in principle, you could just measure the length of the rod when it's at some other temperature, and you can backtrack to figure out how much the temperature changed from 0 degrees Celsius by just reverse engineering this formula. And so that's a way that you can measure temperature. Now, unfortunately, most objects don't actually expand very much when you change their temperature. So it's a little bit hard to measure, but in principle, it's doable. Now, we can continue and get something a little bit perhaps more applicable, which is that objects, or which we obtain by noting that objects expand in more than just one direction. They don't just expand in a straight line, the whole thing gets bigger. So we don't just need to worry about linear expansion. So we need to worry about volume expansion. The whole volume of an object is going to get bigger. So the picture here is you have like a cube, say. This is how we're going to model it. And you increase the temperature. Let's say the side of our cube is L naught. You increase the temperature, and so all of the sides of the cube are going to get bigger. So this distance now might be L naught plus dl, let's say. So how does the volume change? Well, let me write this for a sec. Consider a cube. Well, the volume will change by a small amount. I'm going to assume that these changes in length and changes in volume are very small, just for reasons of calculus. It should become relatively clear in a minute. But the small change in volume would be equal to the final volume minus the initial volume, which would just be L naught plus dl in this case, cubed. Oh, I'm running out of space. Minus L naught cubed. It's a cube, so you just cube the sides. So L naught plus dl is the side of the expanded one, and you cube it. You subtract off the volume of the smaller one, and this is the total. This is the change in volume. Now we can just do this expansion. L naught cubed plus 3 L naught squared dl plus 3 L naught dl squared plus dl cubed minus L naught cubed. So the L naught cubes cancel out. And then we're going to do something that we do often in calculus. So if we're just talking about a small expansion, and these expansions really are small, like we're talking fractions of a millimeter for a few degrees Celsius change, then the length that the sides will expand by, dl, is small. It might be like 1 millimeter. So if dl is 1 millimeter, then dl squared would be a micrometer, and dl cubed would be a nanometer. So these terms, the ones with dl squared and dl cubed, those terms can be just treated as approximately 0, because they're going to be very small compared to this term here, because the small amount is getting cubed or squared and cubed, which makes it even smaller. And so this leaves us with 3 L naught squared dl as our approximate change in volume. And in the limit where dl is infinitesimal, this just becomes exactly true. And so we can rewrite this as 3 L naught cubed over L naught dl. Why would I do that? Well, because L naught cubed is the original volume. So it's 3 times the original volume, V naught, times dl over L naught. But we already know that dl over L naught, we have a formula for that. It's up here. Delta L in this case is dl. So dl over L naught is alpha dt. So this is 3 V naught alpha dt for a very small change in temperature. And so we write this as 3 alpha times V naught dt. And then we call this thing 3 alpha, we call it beta, which is just 3 alpha, which is the coefficient of volume expansion. It's just 3 times the coefficient of linear expansion, but it's just a useful number to keep track of. And so that leaves us that our formula for how the volume changes, dV over V naught, this is how the ratio of the volume changes, is equal to beta dt. And so for small changes in volume, you could just write this as delta V over V naught equals beta delta T. But this is really only strictly true in the infinitesimal limit. But for sufficiently small changes in temperature, this is also good. It's a good approximation. And so this tells us that volumes change. Now, it's hard to measure changes in length. It turns out that there are some clever ways that you can actually detect small changes in length in a different way. So one way to detect a small change in length is with something called an expansion thermometer. Well, these are both, what I'm about to describe are both expansion thermometers, but one of them is, and these are ways that you measure temperature with changes in volume or changes in length. So one method is with a bimetallic strip. That's not how you spell bimetallic. Bimetallic strip. So for a bimetallic strip, you take two pieces of metal, you glue them together real tight, and they're different types of metal. So maybe the one on the left has a high alpha, it has a high coefficient of linear expansion, and the one on the right might have a low coefficient of linear expansion. Now, if you increase the temperature so that delta T is positive, may have missed this, but how do you determine the coefficient of volume expansion? It's just 3 times the coefficient of linear expansion. Then the one that has a higher alpha will expand more than the one that has a smaller alpha. And so the only way that that can happen and then to stay glued together is for the one with higher alpha, or is for them to curve like this. So the one with lower alpha has curved less, or has expanded less because it's on the inside of a curve. And so you could measure the length, and it is different. It is different from its original length by less than the one on the outside. And this is just because the circumference of a circle depends on its radius. And this, so here we have that this one expands less. And so even though the actual lengths are very, very small, the length changes are very, very small, you can get significant curvature of these bimetallic strips when you have small changes in temperature. And in fact, in really old thermometers, not thermometers, really old thermostats, these were actually used, and perhaps even in some modern thermostats, but I doubt it. These were used for determining when to turn on your air conditioning or your heating unit, because the idea is that at some predetermined temperature, it would be straight. And when it got colder than that, it would bend one way. And then the piece of metal would make contact with a part of a circuit that would tell it to turn on the heat. And if it got too hot, it would bend the other way. And that would and then it would make contact with another piece of the circuit that would tell it to turn on the air conditioning. And so you can use this sort of, and then you can adjust the angle and the orientation of that bimetallic strip by turning your thermometer or your thermostat. And so this was like an actual used thing. Another example that you perhaps might be more familiar with is the Mercury thermometer. A Mercury thermometer relies on volumetric expansion. So the point is that in a Mercury thermometer, you have a very, very narrow tube. Very, very narrow tube. And you can make really narrow tubes if you glass blow properly. And you fill it with just a little itty bitty amount of mercury. Well, sorry, you fill it with just a little, you put a bulb at the bottom so that there's a substantial amount of mercury in there. But the tube is really, really thin. And so the point is that at a certain temperature, it will only go up so high. But the bulb at the bottom isn't getting bigger, but the mercury, because there's a lot of it, will expand and take up more space. And so as you increase the temperature, the volume will increase substantially, relatively speaking. But because it can't expand outwards in the bulb, it can only go upwards. And the thermometer itself, the little tube, is very, very narrow. So even a small expansion corresponds to a large increase in height of the mercury. And so this is a way that you can measure temperature by using the expansion of mercury in a thin tube. And the reason we use mercury is because, or the reason that mercury was used, is because it was a particularly convenient liquid metal. Like, we need something that has a relatively fixed coefficient of expansion that doesn't change phases over a wide range of temperatures, like mercury. And it needed to be a liquid so that it could take on the shape of its container when its volume changes. And so that's why mercury was used. Now I think we use bromine or something, but because mercury is not very safe. But the principle is the same. A thing expands. The bulb that stores most of it isn't changing size significantly, so it expands and it has to shoot up the little tube because the tube is really, really narrow. No, it's the mercury, the material inside that. So the tube itself is made of glass, and glass doesn't change shape much when it changes temperature. The key is that the bulb, like the glass isn't changing shape, but there's a lot of mercury in the bulb at the bottom. That's why it has this bulb at the bottom. It doesn't need it, but it makes it more effective. You get larger gradations. And so the point is say the bulb carries 2 milliliters, right? If that bulb becomes 2.1 milliliters, well, the bulb isn't going to carry 2.1 milliliters, so that extra 0.1 milliliter has to fill the tube. And if the tube is sufficiently narrow, that 0.1 milliliter might make it move up a centimeter, right? Even though a milliliter is a very small amount. So the point is that the narrowness of the tube is what lets you read off small changes in temperature as an observable change in height. And that's why, by the way, the mercury always looks so thin in the thermometer. It's not just like a really thick tube. So that's an old way of measuring temperature. Today we have digital measurements, we have infrared measurements and things like that that can measure temperature more precisely and in more interesting ways. But the mechanisms behind those take a little bit more detail than what we have available. So, or than what we can talk about. We can talk about infrared thermometers in a bit, but we won't be able to talk about digital thermometers. Those are relatively complicated. Right. So that's how you can measure temperature. You measure temperature relative to other things, like relative to the temperature that water freezes at or whatever, by choosing a reference point and then measuring the effects that temperature has, and then using material properties to relate that to the actual change in temperature. And then you just put marks on your thermometer that tell you, well, when it gets to this height, that must mean that it's at this temperature because it's expanded this much. Okay, so we're going to continue on with thermodynamics. There's a lot to it. So let's start talking about, so by the way, this is just, so far, all we've talked about is, we've talked very, very little about how energy actually goes from place to place as a result of thermal exchange of energy. We've just talked about the temperature that something has. So now we need to talk about how the energy exchange, entering a system or leaving a system or whatever, affects the thermal energy of the system or the temperature of the system. So to do that requires introducing this notion of heat capacity and phase transitions. Fortunately, that is the next section in the Libre text, so it's a convenient place to continue. This is section 5.3. So up until now, I've been very careful. So first we need to talk about heat if we're going to talk about heat capacity. Up until now, I've been very careful to not use the word heat. I haven't talked about the heat of something or something heating up. At least I've tried not to. If it slipped by, I'm sorry. The point is that the word heat has a very different definition from your everyday layman definition. And the reason I say that is because you might say that, like, oh, this thing's hot, it must have a lot of heat. That's not something that you would say in a physics, that's not something you could get away with saying in a physics class without people pointing and laughing at you, because it just doesn't make sense. As far as the physics definition goes, things don't have heat, and I'll give a specific definition. But another example of this phenomenon where we see a word used in physics in a very particular and rigorous way, like heat, would be the word theory. A theory in physics means something very specific, whereas in everyday language, you'll hear, Sherlock Holmes saying, "Oh, I have a theory," like, and that theory is not at all related to the definition that you see used in physics and science in general to mean theory. So this is just another example. Perhaps heat and theory are probably the two worst offenders when it comes to the everyday language use being different from the use in physics, but unfortunately, that's just the world we have to live in. So make sure that at least when you're thinking about physics or doing physics homework or working on problems or in lecture, when I say heat, make sure you're understanding that word to mean the standard physics meaning. So I haven't given it to you yet, but what I can tell you is that what it's not is thermal energy, which is a measure of the random motion in an object. Thermal energy is not heat. They are not the same thing. Super important. Something has thermal energy, might have a lot of thermal energy if its temperature is very high. It doesn't have heat. So let me define what heat is. So heat is energy that is transferred. I need to get the precise definition here. So it's energy that is transferred from one system to another due to temperature differences or due to a temperature difference between the two systems. So this is what heat is in the physics sense. It is an energy transfer, which is to say, you can talk about heat. You can use the word heat as long as you're saying how much heat is entering that system, because that implies that there's a transfer happening. But what you can't say is you can't say that this thing has a certain amount of heat. Just like work, when you learned about work in 9A, hopefully you learned that work is a transfer of energy. Things don't have work, right? In the same way, heat is a different kind of transfer of energy. Things don't have heat. So let me break this down. So heat, like I said, heat is transferred energy only. Also, it is only caused by thermal non-equilibrium. Meaning you can't have heat transfer or heat flow as a result of anything besides thermal equilibrium or thermal non-equilibrium, i.e. if two things are in thermal equilibrium and they're still exchanging energy, that energy that they're exchanging is not heat. Also, heat also doesn't at all refer to how the energy is transferred. Heat isn't a certain type of energy transfer. It's all energy transfer that happens as a result of thermal non-equilibrium. It's regardless of how the energy is transferred, it's all heat, as long as it's a result of thermal non-equilibrium. So that's what heat is. How do we measure it? Well, just like how you can measure work is measured in joules, we can also measure heat, and heat being a measure of thermal or of energy transfer as a result of thermal non-equilibrium, the SI unit is also energy. And so it's measured in joules, just like thermal energy is. And that's because if you have heat transfer into a system, the thermal energy will often increase by the same amount, all else being held equal. Now, there are a few non-SI units of heat that you may have run into the past. One of them is the calorie, probably the most popular one, but if you live in England or if you've done any work on heating furnaces, you may be familiar also with the British thermal unit, which is the most unimaginatively named unit I've ever heard of, also known as the BTU. So like an internal heating system will say, oh, it has a total heating capacity of 30,000 BTUs or something like that. So that's where that'll come from. Now, a calorie, it turns out, has a relatively nice definition. It is the amount of energy required to add to 1 gram of water to bring that gram of water to 15.5 degrees Celsius from 14.5 degrees Celsius. That's just how much 1 calorie is. 1 calorie is precisely the amount of energy that you have to put into water in order to increase the temperature from 14.5 to 15.5 degrees Celsius. And the BTU is defined in a similar way. I don't actually know exactly how it was defined because nobody really cares about BTUs anyway, but it was defined in a similar way. There's some convention that we all agree on is 1 BTU. And so just like how you can convert feet to meters or how you can convert Fahrenheit to Celsius, there is a way to convert calories and BTUs to joules. And so I should just tell you what that is. 1 calorie is equal to 4.186 joules, and 1 BTU is equal to 252 calories, which is 1,055 joules. Now, just as an aside, the calories that you see on a piece of food, those aren't actually calories. Like, they're not. It's not like if it's 50 calories, or it's not like if it's 100 calories, then it contains exactly 418.6 joules. In fact, food calories are defined as basically how much energy these things release if you burn or digest them. And you know, we store that energy in our bodies by digesting it. But the point is the amount of energy is not 1 calorie per calorie, per food calorie. A food calorie is actually a kilocalorie, or kcal. And if you go to Europe or really anywhere else besides the United States, and you look at the like the food labels, it'll say kcal on it, which stands for kilocalorie. So a food calorie is really 1,000 calories, i.e. one food calorie is like 4,186 joules. And that kind of makes sense. Like we need more than like a few thousand joules to survive per day. We're regularly emitting like 90 watts of power. Like it'll take more than that many joules to function. So there is a difference there. So, but now you know what that actually means. Now you know how much energy is stored in food. Where was I? Right. Right. So that's how we define the unit. Now, if there's a unit, we have units for temperatures. That's good. We have units now for thermal energy and heat. So with those units, we can actually do measurements and do calculations. And so the process of doing these sorts of calculations with temperature and heat and things like that is a process known as, calorimetry. And it involves heat capacity. Now, heat capacity is unfortunately poorly named, and I'll explain why in a minute. So in general, if you have two things that are different temperatures, i.e. if there's an imbalance in temperature of two systems that are in thermal contact, not in, well, we know that there will be energy flow because they are in thermal contact, but their temperature is different, so they are not in thermal equilibrium. And hence, heat will flow because that's how heat's defined. Heat is the energy that's transferred from one system to another due to a temperature difference between the two systems. So heat will flow. And in particular, heat flows from one to the other. And hopefully you guys are aware that heat flows from the hot things to the cold things. Relatively intuitive, I think. And so, in fact, the question then is how much? Like, does one lose more energy than the other? Like, how does this work? And so just by energy conservation considerations, the loss of energy by the hotter system reduces its thermal energy. So it gives off heat. The hotter system gives off heat, and so by thermal energy consideration, or by energy conservation considerations, its thermal energy, the thermal energy of that system, gets smaller. And similarly, the gain of energy by the colder system increases its thermal energy. And in fact, perhaps as you might not be surprised, if these two things are isolated from everything else, then in general, the amount of energy that the hotter system gives off will be the amount of energy that the colder system absorbs. Not surprising, it's just energy conservation. But that energy could in principle go somewhere else if the system was more complicated and so on. So we'll leave that out for now. So this is what happens. We know that the thermal energy will increase will decrease if it loses energy due to heat. And its thermal energy will increase if it gains energy due to heat. So let's just zoom in on just a single system and not worry about where that energy is going or anything just yet. Just so then we can understand what happens. You know, all this talk of thermodynamics is really making this room hot. I'm going to go open my door. I am also turning on my air conditioning because it's quite warm in here. Anyway, where was I? Right. We're just going to consider just a single system. So the question then is, how does heat entering or leaving a system affect the temperature? affect the temperature of that system? Well, we can determine experimentally. Like, you can just go out and do this. You can add heat to a system by putting it on a fire, take away heat from a system by putting it on ice. We see that Q, which is the symbol that we use for heat, is proportional to delta T. So Q is heat. Don't ask why Q was used for heat. I have actually no idea. And so this is just to say that the heat transfer is equal to a constant times the change in temperature. So if the temperature changes by a certain amount, that means that a certain amount of heat has entered or left the system. And if the temperature changes by twice that much, then twice that much heat has entered or left the system. And this particular constant is called the heat capacity. Now, unfortunately, this is a really bad name because the material is not holding any heat in that it doesn't have the capacity to hold heat. So it's named this because the idea is that a substance has the ability, the capacity, to maintain its temperature until a certain amount of heat has been added. So in that sense, it's a heat capacity. Like if you add this much heat, well, you've overgone its capacity by 3 times, so its temperature increases by 3 degrees or whatever. It's just a name though. Often you'll see the word specific in front of it, like specific heat capacity, or sometimes the word capacity will be dropped and you'll just see specific heat. Sometimes you'll see mass or molar in front of it, so it'd be like molar heat capacity or mass heat capacity or molar specific heat, and so on and so forth. These are all just different variations of the same thing. It's just a different constant in front of the delta T for different ways of measuring it. Like if you're measuring it in terms of like, well, how much does it take for 1 kilogram to change its temperature by 1 degree? Well, then that would be mass specific heat. And if you're talking about the heat capacity of a chunk of material, it would just be the heat capacity, and so on. There's different names, and I will go over them. But before we can continue, we need to talk about sign conventions, because implicit into this formula that I just gave you is sign conventions, right? What if the final temperature is lower than the initial temperature? I.e., what if delta T is negative? Does that mean that Q is negative? And yes, that's exactly what it means, actually. So Q is positive implies, or Q being positive means that heat is entering the system. This is a convention that we've decided. So we say that Q is positive, the heat is positive when the energy is entering the system. Now, if you've taken chemistry, you may have used a different convention. By the way, this is heat entering the system corresponds to delta T being positive. So we say that, so we don't have a negative sign here, which is to say that if delta T increases, if the final temperature is higher than the initial temperature, then then the system had positive heat, meaning that energy entered the system. Conversely, if the heat is negative, this means that heat exits the system, which means that the temperature goes down. The final temperature is lower than the initial temperature. So just as a quick aside, in your chemistry classes, I don't know if they still do this, but I know that they did this a few years ago. You guys learned that, well, was it either heat or work? One of those two. But so maybe no, I think it was definitely work. So you guys probably have the same notion in chemistry. Can anybody confirm that, like, that they said that the heat that enters the system is positive if its temperature increases? Or sorry, rather that the Q of a system is positive when its temperature increases. Can anybody confirm or deny that? In chat, ideally. So chemistry has opposite signs for one thing, but it doesn't necessarily have opposite signs for everything. And I think it's work that it has opposite signs for, now that I think about it. Anyway, so okay, so this is the convention that we're going to use here. So please use this convention. That's all I can say. So, so the point here. So this tells us whether Q is positive or negative. It also tells us how Q is related to the change in temperature. But it doesn't tell us like what that constant is, right? Depending on what that constant is, you'll either see wild swings in temperature or very small swings in temperature. So you might reasonably ask, what controls heat capacity? I.e., like, you have a thing. If I hand you, looking for just a chunk of something. don't have I used to just have random bars of copper in my living space when I was an undergrad because I did a lot of machining work, but I don't have that anymore. Okay, well, you guys, here we go. Okay, wooden elephant, just a chunk of wood. This is solid wood all the way through. So you might ask, well, how do we figure out what the heat capacity of this elephant is, right? Like if I increase the temperature by 2 degrees, how much energy will that take? That's a reasonable thing that you could ask, right? And, reasonably, you might guess, well, clearly the size of the elephant matters. If it was like 5 times as big, it would take more energy, but how? How does this work? And so we can actually just understand this by 2 properties. So the first is the type of matter. So the type of matter certainly controls the heat capacity. This is to say, water takes more heat to change temperature than, say, aluminum. So if you have the same amount of aluminum and water, well, the water is going to take more energy, just measurably true. So the type of matter clearly matters. So like we would say, oh, this is made of wood. So we'd have to go figure out the properties of wood, and that would affect our heat capacity. And then the other thing is the amount of matter. Also fairly straightforward. A lake takes more to heat than a cup. Cup of water, that is. Like it just takes more energy to increase the lake by 1 degree than it would to increase the cup of water by 1 degree. So the things that affect how much energy I need to add to this to increase the temperature by 1 degree are its size. So like, maybe its mass would be a good way to do that because clearly its shape probably doesn't matter. And its material. So I'd have to go find the material properties of wood, this particular wood that this is made out of, and then I'd have to measure its volume and perhaps measure its mass, and then I could use that to compute heat capacity in one way or another. And so we can actually just write the equation using those 2 properties. The heat capacity equation. So there's 2 ways that we could write it. One would be Q equals, and so remember, Q is proportional to delta T, so we just need to figure out what that constant is. In this case, one way that we can write it is MC delta T. So here M is mass, and this C, oh boy, this is mass specific heat. So it's the specific heat associated with mass. And so what this tells us is that the amount of, in this formula, the amount of matter, because we know the amount of matter matters, no pun intended, yes, pun intended, the amount of matter is measured by mass. Sorry. I hate, okay, so this is the part of this class that I hate because the names are all terrible. Okay, so I actually prefer the name mass specific heat because the next one that I'm going to give you is going to be molar specific heat, and then they're both specific heats, and then heat capacity is reserved for just the combination of M and C or N and C. However, the convention is that we call mass specific heat specific heat capacity. And I hate this name because it doesn't make any sense. But this is often what you'll see in like textbooks and so on. I'm going to try to use the language of mass specific heat almost exclusively, just so then you know it is the specific heat associated with mass. The reason why this is problematic is because there's another formula that you could write for the same type of thing, which is the heat. So this is the heat that enters or leaves the system, and this is the mass of the system. This is the specific heat, the mass specific heat of the system. And then delta T is the change in temperature of the system. We can do the same thing, but instead of measuring the amount of matter by the weight or the mass of the stuff, we can measure it by how many particles are there? What are the number of moles of the substance? And so we can do that as N, and again, here's a terrible naming convention, but they use capital C for this, delta T. So here, N is the number of moles, and we'll talk about what a mole is in a bit, but it's just a lot of molecules. C is, I will often call it the molar specific heat, because it differs from the mass specific heat, because one is molar, depends on moles, one is mass, depends on mass. But this is often also called the molar heat capacity. I mean, you can probably tell why I hate these naming conventions, because these two things are only different by how they're measured, yet they have different naming conventions. One is a specific heat capacity, and specific refers to an amount of stuff, meaning like per thing, like per mole or per kilogram. And the other one, a heat capacity, refers to the amount for a given sample. So it's just a terrible naming convention, and I'm sorry about that. I prefer these two, and I will try to use those two exclusively. The symbols are also really bad. Sorry about that. Oh, and by the way, in this case, the amount of matter, well, it should be fairly clear. The amount of matter in this case is measured in moles. Now, you might ask, well, why do we have two to begin with? Like why do we, like, if they both do the same thing, they're just measured in different ways. Like one is measured in mass, one is measured in moles. Why might we have both? And it turns out the reason we have both is because for gases, it's easier to measure the number of moles rather than the mass of a gas. Whereas for a solid or liquid, it's easier to measure the mass. So it's useful to have these two different formulations of the same thing, just because like measuring the mass of a gas is not particularly easy, right? Like you need to actually, like you can't just put it on a scale, whereas measuring the number of moles of a gas is pretty easy, and we'll see how that works out in a bit. So these will like there's no reason why you can't use one, like there's no reason why you can't use the molar one for solids or liquids, but it's just typically more convenient because you can just put your sample on a scale to use the mass one rather than the molar one. So, but they're both useful, just in different situations. Now, just as an aside, according to the definition of 1 calorie, we actually can figure out the molar specific heat of water. Sorry, the mass specific heat, not molar specific heat. The mass specific heat of water, also known as the specific heat capacity of water, is Q divided by M times delta T. But we know how, like, we can define this in terms of calories. This is one if you add 1 calorie to water, or to 1 gram of water, and you increase its temperature by 1 degree, well, then you will have input one calorie of energy. And so this formula, 1 calorie divided by a gram 1 gram times 1 degree Celsius, is the mass specific heat of water. It just is. And so you can calculate that, and it's like 4,186 joules per kilogram Celsius, something like that. By the way, just so you're aware, the units for these things are exactly what you would expect. For lowercase c, for the mass specific heat or the specific heat capacity, well, this has units of joules, mass has units of kilograms, c has units of unknown, and delta T has units of, say, degrees Celsius. So you could work out the units of the specific heat capacity just by solving for the units, right? And so it works out to be joules per kilogram degree Celsius or joules per kilogram Kelvin. And the same thing is true for the molar specific heat, which is it's just joules per mole Kelvin or joules per mole degree Celsius. Now, you might ask, well, okay, what? So this is great, right? Well, maybe it's not great for you. The point is why do we care? And so the reason why we care about this type of formula and why this is useful, and actually, you know what? It should just be obvious why this kind of thing is useful. Like figuring out how temperatures change depending on energy is I think, clearly super obvious. But like, even if you're not convinced, this would let us figure out things like, how much energy do you have to add to boil water, right? If you want to get water to boiling temperature, how much energy will that take? Like that's a reasonable question to ask, right? And it lets us solve hard problems. Like, what if you take a bucket of water and then you take like a really hot lump of iron, you add that iron to the water. What is the final temperature of the water going to be? Will it boil? Will it not boil? Like how does this work out? What is the calculation? And you could just compute that directly by using this and what we're going to see in a little bit. And the way we do that is by using energy conservations and the sign conventions that we've already established. You use the energy conservation to say that, well, the energy leaving one system enters the other system. And then you can figure out how the temperatures change as a result of this. And then you conclude that, well, when their temperatures are the same, the energy will stop transferring. And so you can use that to figure out, or you can set up a system of equations so that you have an initial temperature and a final temperature. It's not even really a system of equations. It's just, if you want to know the final temperature of the two systems, they're going to be the same because they're going to be in thermal contact, or they're going to be in thermal equilibrium after energy stops transferring back and forth. And so then you can say, well, the amount of energy that leaves one object to get to this temperature is the amount of energy that enters this object to get to the same temperature. And so this whole process of using energy conservation, using heat capacity and so on to solve these problems is called calorimetry. And there's a lot of examples that I linked to in the lecture notes, so check those out. And I can assure you that there will be a problem or two like this on the homework, and almost certainly there will be a problem like this on the next midterm. So, you know, like calorimetry is bread and butter thermodynamics. Right. So there's one more thing that we're kind of missing in this whole discussion about energy, and that's, well, we know that like if you add you can make one of those out of a coffee. Make one of what? A calorimeter is different from calorimetry. Calorimetry is a process. A calorimeter is a different thing. A calorimeter is a way of measuring the amount of heat that it's a device that measures the amount of heat that something gives off when it undergoes some sort of chemical reaction generally. Yeah, that's well, no, so you're doing, so you were experimentally doing calorimetry, I suppose, in the sense that you could figure out how the temperature, or, no, not even really. Calorimetry it's really like, it's a theoretical process that we use to solve problems. It's not like an experiment. You can perform experiments that would match the outcome of your calorimetry calculations, but like when you add heat to a thing, you're not doing calorimetry. You're just adding heat to the thing. Anyway, so there's one more thing to talk about. So like when you add a hot chunk of iron to a bucket of water, some of it's going to boil, right? So it's not just all just going to change temperature. Some of it's going to change phase. So we need to talk about how heat relates to phases as well. So we need to talk about phase changes and latent heat. So when heat transfers occur, the temperature can change. Like if you just take two things that are relatively close in temperature, like if you just take, I don't know, your phone when it's been running for 6 hours, you put it on your hand, right? Their phone's going to cool down, your hand's going to warm up, but neither of them are going to burn, neither of them are going to change phases. But if you take two things that are far away in temperature or are near a phase boundary, sometimes that heat transfer will result in a phase change. Like if you put an ice cube on a good example of a warm thing, on a stovetop, right? Like an electric stovetop. The electric stovetop is maybe 400 degrees Celsius. That sounds too hot. Maybe 250 degrees Celsius. And the ice cube is really, really cold. So energy is going to transfer from the stovetop to the ice cube. But it's not just going to change temperature. It will change temperature, certainly. But it will also change phase. It will go from solid to liquid. So just to be clear, the phases can change as a result of heat transfer. Now, just to be clear, I think you guys probably all learned this in grade school, but just in case you didn't, the three standard phases of matter are solid, liquid, and gas. There's also plasma, and then there are like quantum phases and so on, but these are the ones that we encounter on an everyday basis. Now, you might wonder, well, don't things just change phase when they get to a certain temperature? Like if you get water to 212 degrees Fahrenheit, doesn't it just boil? And actually the answer is no. So a phase change is a process. It doesn't just happen like that, right? It's a thing that happens. And in particular, during the process, when that phase change is occurring, the temperature of the object is constant. So in particular, heat capacity isn't particularly helpful. Now, let me explain this, because this might seem counterintuitive. How could the temperature be constant if the phase is changing, if you're adding heat? Well, think of it this way. Let's say that you have ice water, right? You have a cup of water, it's a really hot day, so you put a whole bunch of ice in there. So the ice is still ice, and ice can't be above 0 degrees Celsius, right? Like if it was above 0 degrees Celsius, it wouldn't be ice anymore. Ice just can't be above 0 degrees Celsius. But you also have water, and water can't be below 0 degrees Celsius, because if it was below 0 degrees Celsius, unless the pressure is different, obviously, if it was below 0 degrees Celsius, then it would be ice. But somehow you have water and ice existing in thermal contact, in thermal equilibrium. Now, like clearly they're both giving off heat to the environment and to the cup and so on. But like assuming that they were just sitting there together, not giving off any heat to the environment, the ice would just stay ice. The water would just stay water once they both reached the same temperature. Once the ice got to 0 degrees Celsius, it would still stay ice, because it only is forced to become, it's only forced to become water when it's above 0 degrees Celsius. Similarly, once the water got to 0 degrees Celsius, well, there's nothing, like the ice is already at 0 degrees Celsius, so there's nothing to make it freeze. It's at 0 degrees Celsius. It'll only freeze once it's below 0 degrees Celsius. So when the ice and the water are in thermal equilibrium with each other, they'll just both be 0 degrees Celsius. So how do you melt the ice? Well, you melt the ice by adding more heat to the system. By adding more heat to the system, well, the water would want to increase in temperature. The ice would want to increase in temperature, but it can't, because if the water increased in temperature and the ice didn't, then the ice would still be 0 degrees and the water would be hotter. And then that ice they wouldn't be in thermal equilibrium. So the water would transfer energy to the ice. But the ice can't increase in temperature until it is not ice anymore, because it's already at 0 degrees Celsius. If it's above 0 degrees Celsius, it has to be water. So the only way that you can melt the ice is by adding energy to the ice. So this is all to say, and I'm summarizing a lot here, but I'll be more explicit and write stuff down. This is all to say, once say you have ice, you bring it up to 0 degrees Celsius, it will not melt until you add more energy to it. And that energy doesn't go towards increasing the temperature, because you can add a certain amount of energy to it and only some of it will melt and it will still be 0 degrees. Instead, you add a certain amount of energy to it and some of it melts. And you just got to keep adding energy until all of it melts. And once it's all melted, then you can increase the temperature by adding energy to it, because now it's just water, and water, its temperature can be above 0 degrees Celsius. The point is that adding energy can do two things. It can either increase the temperature of a system or change the phase of a system. Can't do both at the same time. For a given material. So there's this kind of sense that, like, as you add energy to a system, like if you start off with a solid, as you add energy to the system, its temperature will increase until you get to a certain temperature. Then you keep adding energy, but its temperature stays flat because it's melting now. And then you add more energy once it's all liquid and its temperature increases. And then its temperature increases until you get to another special temperature where, again, you keep adding energy, but its temperature is not changing. But that's because now it's vaporizing. It's turning to vapor. It's turning into a gas. And so you add energy until it's fully turned into a gas, and then you can add energy and increase temperature again. The point is that there's two separate things happening here. So we need to answer the question, how do we measure the heat required to change phases if we can't use heat capacity? Well, we use a quantity called latent heat. So latent heat is just a measurement, it's just a number for a given material. It is the amount of heat required for, say, 1 kilogram of a substance to change phase. So, for example, so there are two, like in our everyday model of phases, there are 3 phases. So there are going to be 2 phase changes. There's going to be solid to liquid and liquid to gas. By the way, in case you didn't know, when we say it's solid to liquid, that's an object melting. Liquid to solid is an object freezing. Liquid to gas is an object vaporizing. Gas to liquid is an object condensing. The temperatures at which these occur, the solid to liquid temperature, is the same as the liquid to solid. Like they're both 0 degrees Celsius for water. Similarly, the liquid to gas and the gas to liquid temperature, they also both occur at the same temperature. They're both 100 degrees Celsius for water. And this is generally true. And also it's true that the solid to liquid temperature is always lower than the liquid to gas temperature. There are some substances that at normal atmospheric pressures can't actually turn into a liquid for complicated reasons. So they undergo something called sublimation, where they go straight from solid to gas. Carbon dioxide does this, for example. And so there would be a latent heat of sublimation for carbon dioxide at standard atmospheric pressure, for example. But for the most part, when substances can undergo all 3 phases or can exist in all 3 phases, we would have 2 heat equations. One would be Q equals LV delta M. Actually, let's do the first one. Let's do the other one first. LF delta M. So LF is the heat of fusion, the latent heat of fusion. Sometimes the word latent is dropped. And this is just the heat required to take that substance, 1 kilogram of the substance, from solid to liquid. Or the amount of heat that it gives off when it goes from liquid to solid. And then there's the same thing, but for the liquid gas phase change, which would be LV delta M. LV is the heat of vaporization. And it's exactly as it sounds. It's the amount of heat required to go from liquid to gas, or the amount of heat given off when going from gas to liquid. Now, just as a quick, so this tells us how much Q is. And these LFs and LVs, these are just material properties that you go out and measure in a lab. Now, to be clear, delta M is not like, it's not like there's more mass at the end than there is initially. Delta M is not it's not a time delta. It's not like before and after. It's an amount delta. It's how much liquid did you start with? How much liquid did you end with? Because the rest of it turned into gas. So here, delta M tells you how much of the substance changed phase in kilograms. Assuming that your latent heats are measured in kilograms. So for example, if you had water, or if you had ice at 0 degrees Celsius and you added enough heat to melt exactly 1.5 kilograms of the ice, well, then you would plug in 1.5 into your delta M. You would plug in the number for the latent heat of fusion for ice water, and then that would tell you how much heat you added. Now, there is a sign convention that we can use. So if delta M is less than 0, then the liquid is going to solid, or the gas is going to liquid, i.e. you're going down in energy. You're going to this delta M will be negative. You plug in a negative sign for the amount of phase change when your material is going to the lower phase. So if your material, so say you're taking 1.5 kilograms of water and you're having it release heat so that it turns into a solid, well, then you would say that your delta M is negative 1.5 kilograms because your phase, because your material is going from liquid to solid. And then similarly, we say that delta M is positive when you're going from solid to liquid or liquid to gas. So this is all just, these conventions, basically think of them as it's positive if you're going to the higher phase, and it's negative if you're going to the lower phase. That's the way that I think about it and keep it straight. So there's an example now. Now using this, this tool of latent heat, you can actually combine calorimetry, or rather calorimetry is this combination. You can combine these notions of specific heat and the notions of latent heat, specific heat and latent heat to understand how, what am I trying to say? To understand complicated processes that involve phase changes. Like, for example, when you dip your iron into water, some of it's going to boil. And so that involves a phase change that you have to account for. Now, we can combine heat capacity and latent heat to graph the temperature versus the heat added. Heat added being Q for a sample of some substance. I.e., if you add this much heat, what will its temperature and phase be? So this kind of graph, which you'll see again and again, looks something like this for a normal everyday substance that goes through all three phase transitions. Sorry, I'm just trying to draw an actual good straight line. There we go. So we have Q measured in joules here. So this is the amount of heat added to your system. And then you have T measured in Kelvin up here. And so at 0 Kelvin, maybe you have, this isn't necessarily 0 degrees Celsius or 0 Kelvin, it's just some starting point. And then as you add heat, the temperature increases linearly. We're assuming that oh, and let's put the melting point here. This is the temperature. And let's put the boiling point here. By the way, the boiling point is the same as the condensing point. The melting point is the same as the freezing point. These are the temperatures at which these processes occur. So you add heat, you add heat, you add heat, temperature increases until you get to the melting point. But once you're at the melting point, because you were a solid, well then you keep adding heat, but your temperature doesn't change. And so your temperature just is flat until you add a certain amount of heat, at which point all of the substance is melted. But then you can keep adding heat, and now your temperature increases perhaps at a different rate. Maybe it increases faster for a given amount of heat. And so, but then again, at a certain point, your temperature is again constant as you keep adding heat. And then once all of the material has become gas, then it increases again. And maybe it's at a third rate, at a third rates, or a third rate at which the temperature increases. So until you've added this much heat, the object would be solid. And then here, I should get rid of these dotted lines. These are going to confuse people. In this range, you have a mixed solid and liquid phase, because some of it has melted, but not all of it. From here to here, this would be your liquid phase, because all of it has melted, and now you're just increasing the temperature of the liquid. From here to here, at this amount of heat added, you would just be in the mixed liquid gas phase. And then beyond that, you just enter the gas phase. Just keep adding energy, the gas keeps increasing in temperature. Now, we can figure out how thick these, or how wide these ranges are. So the amount of energy to get from, say, absolute zero in this case, perhaps, the amount of energy that you have to add to get to your melting point would be Q times, well, no, maybe not from absolute zero. This would just be whatever this delta T is. It would be Q would be M times C solid. It's the heat capacity of the material when it's a solid. This amount of heat would be Q, would be equal to M times LF. You're trying to figure out how much energy you have to add to completely change phase from solid to liquid, so the latent heat of fusion. This amount of energy would be, well, it's the amount of energy it takes to change temperature. Again, but now the heat capacity would be different. It's the same amount of mass, but now it's the heat capacity, or the specific heat when it's liquid, and you'd plug in the delta T. Similarly, this is another phase change, but here the Q would be the latent heat of fusion times the mass. And then beyond, you would have that the Q, because it's a gas, we're going to use not the mass, but the number of moles. Q equals N times C delta T. And so in these regions, you would use these different formulas. And depending on how much energy you add, you'll end up somewhere else. You'll end up at a different point. So just imagine adding energy tracks you going to the right along this graph. And this, like the shape of this graph is different for different substances, i.e. the slopes and the widths and so on, but their overall shape is the same. And so in fact, you can actually measure things like what is the specific heat of a substance given the slope, right? The slope tells you how quickly the temperature changes relative to the amount of heat added. And you can also use these sorts of things to figure out, well, if I add this much energy to a system that's in this initial phase, where does it end up? And so these are useful. Like these kinds of graphs are a useful way to visualize these things. All right, so I'm going to end lecture there. Sorry, I ran a minute or a few minutes over. And I'm going to open it up to questions.